And yeah, I'm going to be talking about colorful Borsuk-Ulam theorems. And to start off with, we'll talk a little bit about, like, in general, what topological methods and combinatorics are like. Is it possible to move this bar so that?
Yeah, you just take the red-green part and drag it for me. Yeah.
When you're approaching a combinatorics question, a question that's like overall discrete in nature with topological methods, one of the first things that you would want to do is to define a configuration space. So try to set up like a simplicial complex or some type of space where you have all of your possible solutions for your combinatorial question. And then you want to define your function that has a zero that will correspond to your solution. And then the last step is to show that your function has a zero. And there's kind of two big approaches towards doing this process. One of which is using fixed point theorems, of which Brouwer's fixed point theorem is like an example. And this is like the theorem where if you have some continuous map from a d-dimensional ball to a d-dimensional ball, there's some point in that ball that will be fixed by the map so that f of x will be equal to x. This is going to be like one of your ways that you could show that like your function has a zero, or to like isolate what your actual solution is. And the kind of other big class of methods that you can use are kind of more equivariant methods. And so an example of like a theorem you would use if you're leaning toward the equivariant methods is the Borsuk-Ulam theorem. And that is the one that's in the name of my talk. And so that's one of the ones that we're going to be focusing on a lot today. So the Borsuk-Ulam theorem says that for every continuous odd mapping f from the d-dimensional sphere to d-dimensional Euclidean space, you have some point in the sphere that gets mapped to zero. And by odd mapping, what I mean is that f of minus x is equal to minus f of x. And that's also like how that equivariance is coming in, because it's the equivariance of the group action of applying that like -1 that is like your non-trivial elements in C mod 2. This. And so it's equivariant because we can switch the order of the function application and the action of the minus sign. And what this looks like is if you have like your North Pole and South Pole on a sphere, then you want f of the function applied to the North Pole to map to the negative of f applied to the South Pole. And so that there's like this like symmetry of like just switching the poles of your spheres, which you can do in any division. And in terms of like the colorful aspect of the Borsuk-Ulam theorem, there's a lot of colorful generalizations that exist for various theorems in fixed point methods. But there's not the same type of colorful framework that is like applied consistently in the more equivariant methods. So our goal today is to set up what that framework can look like and how to get colorful generalizations whenever you're using an equivariant method. Any questions thus far? And also feel free to interrupt me at any time if you have any questions. So to look a little bit about like what a colorful generalization looks like, we'll first look at the KKM theorem, which this is an analog of the Brouwer's fixed point theorem. So this is something that's more in the fixed point theorem methods, and thus it has some colorful generalization. So we'll get to see what this looks like. So if you have some open cover, although in my picture it's kind of a closed cover, of the d-dimensional simplex. So d-dimensional simplex, we have our vertex for the 0-dimensional simplex, an edge for like 1-dimensional simplex, triangle for 2, tetrahedron, and so on. And you have an open cover that has 1 through d+1 different sets covering it. So that's 1 for each of the vertices that you would have in any of these simplices. And you have the criteria that for any subset of these d+1 vertices, so this is like the set 1 through d+1, that defines a face. And that face should be covered by the union of all the sets that are indexed by the vertices that are in that face. So for example, if we have like this red and yellow set are like 1 and 2, the edge 1, 2 should be covered by A1 and A2, which are the red and the yellow set. in that case, you have a non-empty intersection. And this ends up being very much analogous to Brouwer's fixed point theorem, because you can classify each set by like which coordinate is increasing when you're applying your function. Like if you're going from a simplex to a simplex, you can encode each point with like barycentric coordinates. So 3 different points that all sum, 3 different coordinates that all sum to 1, and that encodes something in the simplex. So like 1, 0, 0 for each of the vertices, or 1, 0, 0, 0, 1, 0, 0, 0, 1, 1/3, 1/3, 1/3 in the center, and so on. And whichever coordinate is increasing, you can say that that's like the set it should belong to, or with some type of tiebreaker thing. And you can get a colorful generalization by having d many copies, or like d plus one many copies of this thing happening. So you had one open cover before, now we have d plus 1 different open covers. And that's our like different colors. So like our first color, second color, and third color. And what we want is that the criteria that the original thing satisfied should now be satisfied by something that takes representatives from each color. So the colorful KKM theorem says if I take the yellow set from my first cover, the red set from my second cover, and the blue set from my third cover, they again must have a non-empty intersection. And when I have all the covers are exactly the same, I get the original theorem back. And that's why it's a proper colorful generalization. So this has been like a super useful theorem, because the colorful KKM theorem, that is something that proves like fair rent division and a lot of other interesting problems, including like piercing of convex sets in the plane, and a variety of other applications. And like getting more and more colorful generalizations has helped connect more and more results. So like there was a new colorful generalization result that came out recently that connected this to colorful Caratay-Adori's theorem. If you know of colorful Caratay-Adori's theorem, which had not been a previous connection between the Brouwer's fixed point theorem and colorful Caratay-Adori's theorem, as a result by my advisor.
So what do the KKM mean?
So KKM is, I probably should mention that. KKM is Knaster Kuratowski Mazurkiewicz. So 3 Polish mathematicians who proved this generalization. And then the colorful one was proved by David Knapp in the late 80s. And yeah. Any other questions? So here's like kind of how colorful frameworks work for our fixed point methods. In equivariant methods, we don't have the same type of framework. So just to kind of look at another result that links to the equivariant methods, there's the topological Radon theorem. And this is a result of that's equivalent in a lot of ways to the Borsuk-Ulam theorem. And I'm going to be talking a little bit about how this ends up connecting in a kind of surprising way to the KKM theorem. And then we'll start talking about how to make things colorful. So for the topological Radon theorem, if you have a continuous map from the D simplex to RD minus 1, then you have to have a Radon partition. And what the Radon partition means is a partition of the vertices in such a way that the convex halls of those vertices will intersect. So here I have a tetrahedron that has been mapped into R2, which is our TV screen. And the Radon partition in this case would be taking like our top vertex that's like in front of us, and then like the whole face that's all kind of the backmost face. And these intersect at the vertex, so that like satisfies the Radon partition. It's disjoint vertices, so it is a proper partition. I could have mapped it to R2 in a different way, in which case my Radon partition would be the 2 edges. So with a topological Radon theorem, there's not really a like straightforward or like known colorful generalization of this. but we will hopefully have enough time to get to that. And something that is known at this point that my advisor and I showed is that you can actually set up a duality between the KKM theorem and the Radon theorem. Given that the Brouwer's fixed point theorem is actually a corollary of the Borsuk-Ulam theorem, that's not entirely surprising, but it is nice to be able to get the equivalence between the two. And the way that we can do that is by, instead of just viewing our covers and the partitions in one way, we instead view this partition of unity subordinate to the cover. And this is where I'm going to be using the chalkboard a little bit. And so what I mean by a partition of unity is that for these different functions that go from our D simplex to 0, 1, they satisfy the criteria that for all of our functions applied to any x in our simplex, they all sum to 1. And that's like just the unity part. The subordinate to aspect is that alpha I of x is greater than or equal to 0 if and only if x is actually in that other set AI. And
so the alphas reflect the support of his set spacing.
yeah, it's a way of just like saying basically an indicator function of a lot of these partitions, but with like different values so that it's always summing to 1. And then when we view this that way, we can say that like any set of alphas from alpha 1 to D plus 1 that act as a map from the D simplex to the D simplex, since they sum to 1, we can just use them as coordinates, that you will either have a Radon partition or you have a non-empty intersection. And that's how we end up with this duality between the two. And we'll hopefully also be able to talk about the colorful generalization of this, which then gives us back the colorful KKM theorem and gives us an analog of like colorful Radon and stuff. Any questions? So now I'm going to finally get to the actual colorful aspect of like, how do we come up with a good colorful generalization of a statement about functions that has previously been a little bit more elusive. So to kind of get a good sense of whether our generalization is a good colorful generalization and is giving us interesting things, we're going to look at the more specific case of the ham sandwich theorem, which is again another one of these results that is connected to the Borsuk-Ulam theorem. And what we're going to be using is a set of finite Borel measures where any hyperplane has measure 0 according to these measures. And that is what we'll call a mass. And then the ham sandwich theorem says that any D masses in RD has some hyperplane that perfectly bisects them. It's the same hyperplane throughout. And this is related to the Borsuk-Ulam theorem because you can encode each hyperplane as a point on the sphere. And using the Borsuk-Ulam theorem, you can show that you would have to have this hyperplane that bisects them. And this is how we'll like kind of develop our colorful generalization. So to find a colorful generalization, we can first just look at the simplest case to make sure that we are developing something good. And so we'll look at when D is equal to 2. So the first thing we'll need is we'll need 2 sets of masses. So 2 masses in each set, because it's D masses in R2, and then 2 sets of them. So there are 2 different colors, 1 and 2. And something that you might want to have is you would say that there exists some line H such that at least half of your first mass is on the positive half of the half space. And then at least half of the B mass in the second color is on the positive half space. So you're getting like kind of a diagonal, like in the same way that we had the red and yellow before. We have the first one has the A set, the second one has the B set. And then you want the opposite to be true for the negative half space. So you have at least half of your A2 mass in the negative half space and at least half of your B1 mass for your negative half space. If we set these two measures equal to each other, so A1 equals A2, then that would mean that this is bisected. We get the original ham sandwich theorem back. It's colorful, it's a ham sandwich theorem. So that seems like a pretty nice direction to go in, but unfortunately it is false. If we arrange our masses along the moment curve, and in R2, this is going to be just the parabola, then any hyperplane is just going to intersect it in exactly 2 points. So we can kind of consider our masses without loss of generality for A1 and B1 to just be arranged in this way. And we can just cut our half spaces independently using the moment curve. So for A1 to have at least half of its mass in the positive half space, if we call this middle part the positive half space, so like thinking about it like this way, then the first cut has to be here or to the left of it to get half of that. And then looking at our B1 criteria, to have at least half of the B1 mass in the negative half space, our second cut has to be here or to the left of it. If this is the case, we can arrange our second set of masses adversarially so that we can never actually get the partition to satisfy these two criteria. So that's unfortunate. If this didn't work, well, we can relax things a little bit. We can be a little bit more flexible, and maybe that will give us a colorful generalization. So now, instead of the like more strict criteria that I said before, we have our two colors of masses and the A and B masses in each one. And we'll say that there's at least half of the A1 mass in the positive half space, at least half of the A2 mass in the negative half space. And then either B2 has half of its positive mass in the positive half space, and B1 has half of its mass in the negative half space, or kind of the reverse. So you have B2 mostly in the negative half space and B1 mostly in the negative half space. But in this criteria, like if this is our conjecture of a colorful generalization, well, then you end up with something that's basically trivial whenever the first ham sandwich cut is done. So in one case, we got something false. In the other case, we got something useless. So this isn't looking great, but I am giving a talk here. So there is a happy ending. What we're kind of missing is that we keep on trying to force this to be like 1 and 2 with like the D masses in our D. But there's a extension of the Borsuk-Ulam theorem called Kaifon's lemma, which allows you to have a little bit more flexibility. It kind of builds in a few extra labels. So Kaifon's theorem is a statement that's about triangulations on the sphere instead of functions, but you can take like limits of like how these triangulations work and then just get something that is a very similar statement to Borsuk-Ulam. And so what Kaifon says is that if you have some centrally symmetric triangulation so that you can still satisfy this like oddness with a vertex set V, some label set that's 1 through D plus 1 with signs that are plus or minus, and the labeling math is odd. So L of minus V should be minus L of V. So you might notice that like 1 and minus 1 are on opposite poles. 3 and minus 3 are on opposite poles. You need that symmetry all throughout your triangulation. Then you are either going to have that there's some edge that has minus J and plus J, or you're going to have a facet. So top dimensional face, like a triangle or tetrahedron, depending on or the higher dimensional simplex, depending on the dimension of your sphere, that has all of the labels with any signs that you want. In the original Kaifan statement, he said it was alternating signs. It's not that different to prove it with just whatever signs you want. And so that's the one that we're going to be using because it's a little bit more useful in our circumstance. So it has these kind of two options, one of which is our edge case. So you have a minus j plus j. So like, for example, this like -2 + 2 edge. If we avoid those edges in every case, you must have this top dimensional face of 1, -2, 3, or you could have 1, 2, 3. There's like the triangle that's kind of in the back there that like satisfies that. Any of the signs you want. This gives us back Borsuk-Ulam. Whenever you have just 1 through D labels, you can use like your continuous function on the sphere to say like, what is my maximum magnitude coordinate? And that gives you some type of labeling with just 1 through D. You can't get the top dimensional face, so you get the edge, and then slowly that edge gets smaller and smaller, and you get a limit of points in a compact set, so you get your 0 that you want for the Borsuk-Ulam theorem. And when you have more than D labels, you have a slight extension and generalization. And this is exactly the amount of flexibility you need to get a colorful generalization of the ham sandwich theorem that is not false and not trivial. And the way that you do it is by first trying to generalize it into a Kaifan style ham sandwich theorem, and then going to a colorful ham sandwich. So the Kaifan style ham sandwich theorem that you would say is that now you have 3 masses in R2, or D plus 1 masses in RD, and you get a line H such that the mass of the A mass in the positive half space subtracted by the A mass in the negative half space, so the difference between like the masses on either the plus or the minus side, is equal in A, B, and C. So note, if I set C equal to 0 all the time, like it's just a 0 measure and it's not a very interesting mass, this difference has to be 0. And therefore, BH plus and BH minus has to be equal, which means that we bisected the masses with our hyperplane. And so, or our line. So if you just set C equal to 0, you get original ham sandwich back, kind of in the same way that Kaifan extends Borsuk-Ulam. Any questions about this? Right. Now with the 3 masses, we can actually get a properly colorful ham sandwich where I now have my 1, 2, and 3 colors with A, B, and C masses each. There's 3 families of masses. You have some line such that either one of A, B, or C has all of its mass in the positive half for one of the families, and the minus half space for the other family. So like, for example, like if B1 is almost entirely in the half space and B3 is almost entirely in the minus half space, that is like what this would be. Or you're going to get a permutation such that you have the A1 mass is maximized, so you have the most A1 mass of any other of the masses in your first family. The B2 mass is maximized in the second family, and the C3 mass is maximized in the third family. And this is kind of echoing this Kaifan statement again, where you have either this like -2 + 2 label, or you have your full dimensional face with all the different labels. And in terms of like sandwiches, the type of statement you're saying is that instead of just cutting a sandwich and having it bisected, you're saying with a single cut, I have my red, green, and blue sandwich, and I have the most red bread and the most like blue cheese and the most green ham. And like you have like some type of representative sandwich that is mostly sampled on this like positive half space. And this degenerate or kind of degenerate case of like when you have just the entirety of your red bread on one half and your entirety of your blue bread on the other half. It's actually a very useful case in terms of ham sandwich theorems, because it means that you are trying to make it so that your three different families of masses are distributed in kind of a similar way. You don't want any of them to be entirely disjoint from each other. They need to be somewhat related, actually contained in a sandwich form, and not just floating around as a bunch of ingredients. So that's colorful ham sandwich in R2. I'll talk a little bit more about like general colorful Borsuk-Ulam, but before I move on, there is a rather surprising aspect, which is that the Chi-Fon style ham sandwich on its own already has a lot of interesting implications. We can say that this result by Bárány, Hubard, and Jerónimo from 2008 about unequal partitions of masses is actually a corollary of our Chi-Fon style ham sandwich. So if you have mu1 through mu d, d masses in Rd, with well-separated supports, so that just means that there's no hyperplane that goes through all d masses. And you have alpha 1 through alpha d telling you how much you want from each mass. So like I could have like 1/2, 1/2, maybe a quarter, maybe an eighth or something like this. Then you have some hyperplane such that you have exactly the amount you want. So like 1/2 of your first mass, 1/4 of your second mass, 1/8 of your third mass, and so on, for all of your masses at once. And the way that you can get this as a result of your Chi-Fon style ham sandwich theorem is you use the fact that you have this extra mu d plus 1, this additional mass that was not previously in the statement. You get this kind of really other well-separated area, and you say that you scale up each one so that the amount that you want to take from like your first mass, the amount you want to take from your second mass is equal to each other in this scaled up world. And it's also equal to our third mass that we've artificially added. No hyperplane can go through all three masses in R2. So that means that in order for this like difference to be satisfied, one mass has to be entirely to one side of the hyperplane. And so it tells you that you're cutting off exactly the amount you want from each of your other masses. So that's a fairly nice corollary. It's a bit non-trivial to say that you can always add in this d plus 1 mass, but in the original proof of Bárány, Hubard, and Jerónimo, there's kind of like an analogous like difficult statement, and like they're both like it's not that we're secretly using this again to say that we can add in this like well-separated mass, but like it's a nice way of being able to show this a nice alternative proof to this Bárány, Hubard, and Jerónimo result. All right. So now for the actual statement of the colorful Borsuk-Ulam theorem, which if we want to apply this any place where you can apply the Borsuk-Ulam theorem, there's a lot of them. There's like a whole book by Jerónimo using the Borsuk-Ulam theorem of places you can apply it. If you can get a Chi-Fon statement, Chi-Fon style generalization, you can then also get your colorful generalization basically for free by like using the same framework. And the way that you phrase it is you say that for any odd continuous map from the D sphere to the space of d plus 1 by d plus 1 matrices, you have an X such that you either have a column that has a row that's maximized in I and a row that's may have a typo there. Oh, the jth coordinate like maximizes row I and it maximizes row L at the same time, but in like the negative, it maximizes in a negative way, so that the absolute value is the maximum, but like negatively. or you get a permutation such that you have your different maximizations in each row and in each column. So you're either going to get something where like 10 is the maximum in this row, and 7 is the maximum in this row, 8 is the maximum in this row, so we have all three, so we're good. That would be an example of a good value for this X. Or you're going to end up with this 10 is the maximum absolute value in this row, 7 is the maximum absolute value in this row, but -7 that like works out in terms of these maximums. And it's just, again, kind of relating to this Chi-Fon statement. Is that a question or?
Yeah.
Okay, sorry. Yeah. And yeah, and this is also how we get our like colorful ham sandwich. You just set up the different like families of masses to be our measures for like our array in a matrix. So as I was mentioning before, you can then also show that there's a colorful generalization of the duality between KKM and Radon. And this just means that we have now our D+1 different families of partitions of unity, and we have our like face structure, and then we have an X such that we get a maximized value for each J, for each I that we're applying the permutation to. And this does give us back our original colorful KKM theorem. The other interesting aspect of this is I don't include a note about like our kind of edge case, because in the Radon case, you don't actually end up ever being able to get a case where you have a maximized in a positive and negative way at the same time. And I think I still have a decent amount of time. So unless there's any questions, I might talk a little bit about how you actually like kind of go about proving the colorful generalization, because it uses a lot of these similar methods from fixed point theory, and it's a rather nice way of proving things. Are there any questions before I move on? Right. So one of the ways that you can prove colorful generalizations, like of the Brouwer's fixed point type of results, is you kind of switch between Sperner's lemma, which has this like statement about colorings of specific vertices in a triangulation, and the KKM theorem, which has the set covering. Chi-Fon acts as our labeling type of statement, and then we also have our set covering statement. So you can talk about a set covering version of Chi-Fon, and he did in his original paper as well, where you have your different open or closed sets, you can say either one, and you have their negatives, and these sets all have to cover your sphere. And as long as there's no intersection between AI and minus AI, then you have to have an intersection of all the different AI with some fixed signs that you can fix to be whatever you want at the same time. You could fix them to be alternating signs, you could fix them to be all positive. And then the next step is to get your colorful set covering version, where now you, in the same way that you had the colorful KKM sets where you have your J different covers, you have your D+1 different covers, each satisfying this criteria. So each one covers the sphere, and then you have this intersection criteria where there's no AI and minus AI that intersect from the Jth cover and the Lth cover. And if that happens, then you have to have some permutation where the pi of ith cover, the pi of ith set from the ith cover with fixed signs has a non-trivial intersection. And this is the key part of proving the Borsuk-Ulam theorem. And the way that you can get this is just by first considering any triangulation of your sphere. And when you get your triangulation of the sphere, then taking the barycentric subdivision of this. So this is where for every dimensional face, I have some vertex that corresponds to that face. So I have the vertex here, the orange one that corresponds to the triangle of this, the two-dimensional cover. The red vertices each correspond to the edge. And then you have the blue vertices corresponding to the original vertex. And any face corresponds to a kind of like a flag of faces. So 1, 1, 2, 1, 2, 3, each kind of being included in the other. And when you take this barycentric subdivision, you get this nice automatic indexing of each of the vertices in the barycentric subdivision, where they have like a dimensionality associated to them. So this is like the in the barycentric subdivision is a 0-dimensional vertex. This is a 1-dimensional vertex. This is a 2-dimensional vertex. And you can use this to get information from all of your coverings at once, where in the in each vertex you say, okay, ask the first cover, if I'm in a 0-dimensional vertex, what label I should give this. So if it's in the first label, or if it's in the -2 set of the first cover, then I'll label it with -2. This one, I look at the second cover. If it's in the third set of the second cover, I label it with 3, and so on. And then I can apply my original Chi-Fon statement, and I know that I have to have a colorful triangle that has all different labels of whatever like fixed signs I asked for, or this edge. But I can always take a fine enough triangulation that I never end up with the edges. And so I just end up with these like top dimensional triangles. And if I have a bunch of these triangles, I can take some point in the middle to be like a sequence of points. And as I get finer and finer triangulations, I get a converging sequence of points that gives me my non-trivial intersection of all of these sets and gives me my colorful Chi-Fon statement. And then using the set theorem, it's fairly easy to prove the Borsuk-Ulam statement, because you can just define each set to be like where each coordinate is maximized. So the Aij set is when the jth row is maximized by the ith column. And the minus Aij set is when the jth row is still maximized by the ith column in magnitude, but it has a negative sign. And as we go, that gives us the intersection criteria for our colorful Chi-Fon. Have our two different rows respectively maximizing things positively and negatively in our same column. And that is everything I wanted to talk about. So thank you for listening.